In this video, we'll continue to look at electricity. In this particular video, we'll be looking at IV relationships, or more commonly referred to as IV characteristics, and we'll of course be paying attention to certain devices as indicated by the syllabus. So we'll look at the IV characteristics of metallic conductors at constant temperature, filament lamps, semiconductor diodes, and of course lastly solutions of copper sulfate in water using copper electrodes. Now this circuit basically shows a typical circuit that can be used to investigate the IV characteristic of any electrical component as indicated in that list there, right? So basically this is a circuit which is commonly used. So we have essentially a battery, and in that circuit we also have a Weber resistor which acts as a potential divider. So what this does, it basically allows us to vary the potential difference or the voltage across the device that we're investigating, which is typically connected between these two terminals X and Y, right? So for instance, if it's a metallic conductor, we'll connect it between X and Y. We'll adjust the position of the slider or the wiper terminal on the Weber resistor, and in doing so, we'd vary the potential difference across the component, and of course, we'd measure the corresponding current, and so we get the voltage and the current. And the characteristic, or the IV characteristic, is of course typically a graph of current plotted against voltage, right? So the IV characteristic of any component is basically a graph which shows how the current flowing through the component varies with the potential difference or the voltage across the component, and it is normally done in what we call forward direction as well as reverse direction. What exactly does that mean? If we take a piece of wire, let's say this is representing a piece of wire, we connect it in one direction between X and Y to give, say, the forward characteristics, and then of course we open the circuit and then we reverse the component, and we then treat those values or those set of results as the reverse characteristics, and we basically show both when we plot the graph of current against voltage. Usually the values in the forward direction are treated as being positive, and the values in the negative direction or the reverse direction are treated as being negative. So we could say that this is basically, say, minus I and this is minus V, right? So again, this is a circuit that we normally use. So we have the battery, have a Weber resistor which will be functioning as a potential divider. We have a voltmeter to measure the potential difference across the device, and of course we have a current measuring an ammeter rather, measuring the current flowing through the device, which will be placed between X and Y. So let's first examine the IV relationship or the IV characteristic of a metallic conductor. So once again, we would have actually conducted the experiment which shows the IV characteristic of the metallic conductor, and therefore this one should not come as any surprise. So the IV characteristic of a metallic conductor at constant temperature is essentially a straight line passing through the origin, right? So the IV characteristic of a metallic conductor at constant temperature is a straight line passing through the origin. And what this basically shows is that the current I is proportional to the voltage V, right? So based on this straight line relationship passing through the origin, then this basically tells us that the current I is directly proportional to the potential difference V across the conductor, right? And this of course is where we get Ohm's law from. Now according to Ohm's law, the current through a metallic conductor is directly proportional to the potential difference across it, provided that temperature and other physical conditions remains constant, right? So once again, according to Ohm's law, the current through a metallic conductor is directly proportional to the potential difference across it, provided that temperature and other physical conditions remain constant. And basically this can be summed up based on this straight line relationship passing through the origin. Now Ohm's law is often expressed in the form of an equation. V is equal to IR, right? So this equation of course occurs as a consequence of Ohm's law, in that the current is proportional to the PD, provided that temperature and other physical conditions remain constant. Now from this equation, V is equal to IR. If we make I the subject, I is equal to V over R, and we can write the equation like this: I is equal to 1 over R times V. Now basically, if we were to plot a graph of the current against voltage, then essentially the gradient of that graph will give us 1 over the resistance. and therefore we can actually look at the graph and tell how the resistance of the particular component is changing, if it is changing. So the gradient of this graph would be said to be uniform or constant, and because the gradient is uniform or constant, what it represents, 1 over r, is also uniform or constant, and therefore for such a graph the resistance is uniform or constant, right? So basically this shows that for a metallic conductor at constant temperature, the gradient of the IV graph is uniform or constant, and therefore the resistance of that particular device is also uniform or constant, right? So it is important that we specify constant temperature, because if the temperature of the conductor is not constant, then it means that the resistance will not be constant, and this graph of current and voltage will not be a straight line passing through the origin. If the resistance is changing, so will the gradient of the graph, and therefore it will no longer be a straight line. So of course it is important to not just specify a metallic conductor, but a metallic conductor at constant temperature. Good? Now, having gone through that now, let's now look at the filament lamp, right? So once again we say that this equation V equals IR is essentially a consequence of Ohm's law, but not the law itself. So in an exam, if you're asked to state Ohm's law, you're not expected to just write down IV equals IR or any other version of this equation. What you're expected to do is to write out the worded statement. The current through a metallic conductor is directly proportional to the PD across it, provided that temperature and other physical conditions remain constant. So that is what Ohm's law states. This equation is simply a consequence of Ohm's law, but it is not the law itself, right? Good. Now the next, by the way, we did mention about forward or reverse characteristic, and we said that basically you would basically connect the component in one direction for the forward, and then for the reverse you simply reverse it, right? And in the case of the metallic conductor, no significant change is observed. We still get a straight line passing through the origin, but of course we treat the reverse values as being negative. Good. Now let's talk about the filament lamp. Now the filament lamp as an IV characteristic, which in some part resembles that of a metallic conductor. So let me just draw it properly. Right? So this is now the IV characteristic of a filament lamp, right? So we can basically see that within a certain region, the graph is a straight line passing through the origin. So within this region right here, the graph is a straight line passing through the origin. And what exactly does it mean? It basically means that within this little region, it is obeying Ohm's law. And what exactly does Ohm's law state? I'll state it again. The current through a metallic conductor is directly proportional to the PD across it, provided that temperature and other physical conditions remain constant, right? So for a metallic conductor is often referred to as an ohmic conductor, and that simply means it obeys Ohm's law, right? So within this region, we can see that it is a straight line passing through the origin, which means the current is directly proportional to the voltage, and Ohm's law is obeyed. So this region is often referred to as the ohmic region, right? So within this region, once again, we say that Ohm's law is obeyed, and therefore we often refer to this region as the ohmic region. Simply because within that region, Ohm's law is obeyed. Now, outside that region, what do you notice? The graph is no longer a straight line, but it starts a curve. It starts to flatten. And why is that? Now, you have to remember that basically with a filament lamp, the filament is a thin piece of metal, and of course, as current flows through the filament lamp, the current, due to the heating effect, will cause an increase in the filament resistance. So basically, within this ohmic region, the temperature of the filament basically remains constant. However, outside of that region, the temperature will start to increase. And because the temperature increases, the resistance will increase, and this will mean that basically there's going to be a smaller increase in current for a particular increase in voltage. If you remember, electrical resistance is basically an opposition to the flow of an electric current. So in other words, then, when you increase the resistance, then you'll end up with a smaller current flowing. And this is basically what is being shown here with this IV characteristic for the filament lamp. So once again, to summarize, at small currents, basically, relatively small currents, the current is proportional to the voltage. Ohm's law is obeyed. In other words, it behaves like an ohmic conductor. However, at larger currents, the temperature of the filament increases, and so does the resistance, and this results in the graph curving, as there is now a smaller increase in current for a particular increase in voltage. And just as before, as I said, we normally examine this in forward and reverse. So this is the positive values once again represent the forward characteristic, and the negative values represent the reverse characteristic. And essentially, the characteristic is the same whether forward or reverse, but of course, we treat the reverse as being negative so as to differentiate between their values and those taken in the forward direction. Now, the third device we will examine is the semiconductor diode. Now, this is a symbol for a semiconductor diode. It's a little triangle, a little thing at the end, right? So this will be the positive end, that will be the negative end. So this is said to be, this is a symbol for a semiconductor diode. Now, what exactly is a semiconductor diode? Without going into too intricate details, a semiconductor diode is essentially a device which is only allowed to conduct electricity in one direction, and that is when it is said to be forward biased, right? So a semiconductor diode conducts electricity in one direction, which is said to be forward bias. It does not conduct in opposite direction, which should be reverse bias, right? Reverse bias or forward bias, right? Now, what exactly does reverse bias or forward bias mean? Let's use a simple circuit with a battery and explain when a diode is forward bias as opposed to when the diode is reverse bias. So let's examine this circuit here. We have a battery, and we're going to connect a diode to that battery. Right? So this is the positive terminal of the battery, negative. Positive terminal of the diode, negative. Now, in this particular case, we have the positive terminal of the diode being connected to the positive terminal of the battery. And we have the negative terminal of the diode connected to the negative terminal of the battery. So this would mean that this diode is forward biased, and therefore the diode conducts. So the diode will basically allow the passage of an electric current because it is forward biased. However, if we were to simply reverse the polarity of either the battery or the diode would no longer be forward biased. It will be reverse biased, and it would not allow the conduction of any current or any significant current. So let's do that. So we're going to keep the battery's polarity and reverse the polarity of the diode. So now we have the positive terminal of the battery connected to the negative terminal of the diode and vice versa. And therefore this diode is now reverse biased. And we say that it does not conduct. Right? So in reverse bias, the diode essentially does not allow the passage of an electric current. So we did mention that we have to basically connect the device in one direction, in forward, and that's in relation to the polarity of the battery, and then we must reverse the connection in order to get it in the reverse. So based on the polarity of this battery right here, the positive terminal is right here, then in connecting this diode in forward bias, then the diode would basically look like this. Right? So this would basically be in forward bias, where the diode would conduct, and then of course we would then reverse the polarity and put it in reverse bias, and of course we would not expect it to conduct. Right? So the IV characteristic for a semiconductor diode typically looks like this. Simplified. Where should I put it? So the IV characteristic for a semiconductor diode typically looks something like this. So again, we have I against V. It looks something like this, right? In some books, they may show a tiny current, we'll call a tiny leakage current in the reverse bias characteristic. But in some books, they might not even show that, right? So in some books, they may just show the current is basically flowing in the forward bias direction, and they basically would not show any in the reverse. But of course, it is not uncommon to see a small current in the reverse bias direction, something like that. And what we need to also to understand, in some cases, in the forward direction, the current is of the order of milliamperes, but in the reverse direction, this will be of the order of microamperes. So basically then, it even goes to show how much smaller the reverse current is compared to the forward current, right? So this is essentially the typical IV characteristic of the diode. Now, what we must also understand about a semiconductor diode, the diode only conducts when it is forward biased. However, there is a small voltage that the diode must be, which the diode needs to surpass in order to conduct, right? Depending on the particular type of diode, it may be about 0.6 volts for most, right? So it usually ranges from about 0.3 to 0.6 volts, depending on the particular type of diode, right? That is normally referred to as the cut-in voltage, right? So basically then, the diode essentially only conducts a significant current in forward bias, but in order for it to conduct, the voltage across it must reach this cut-in voltage, and then there's likely to be a significant increase in the current for only a small increase in the voltage. So there we have our IV characteristic for semiconductor diode. We explain what it means for the diode to be forward biased, or what it means for it to be reverse biased as well. Lastly, we want to look at the IV relationships for solutions of copper sulfate in water using copper electrodes. Now, clearly, we're talking about a solution here. So, this circuit will have to basically connect the circuit to the electrodes, which are basically immersed in the liquid, right? And of course, it also do forward and reverse by interchanging the connections. But we'll basically look at the IV characteristic for this particular case. Now, essentially, a copper sulfate solution with copper electrodes, the characteristic basically looks like this. Right? So, essentially, we can say that it is ohmic. Based on the fact that it's a straight line passing through the origin, the IV characteristic for a copper sulfate solution using copper electrodes basically is ohmic. In other words, then it behaves exactly as an ohmic conductor would, or metallic conductor at constant temperature. The graph of current against voltage is a straight line passing through the origin, which basically tells us that the current is directly proportional to the potential difference across it. All right. So here we're able to look at the IV characteristics, or the IV relationships for these devices as required by the syllabus.